Good evening, people. Tonight, we are diving into Advent of Code Day 18. As you can see, I'm behind. It's almost midnight. Day 19 is about to be unlocked, but I am on day 18, so here we go. All right. So I'm going to change things up a little bit. Not going to go through the whole story, but we're going to get to the point. Day 18, Lava Duct Lagoon. Thanks to your efforts, the machine part factory is one of the first factories up and running since the lava fall came back. However, to catch with a large backlog of part requests, the factory will also need a large supply of lava for a while. The elves have already started creating a large lagoon nearby for this purchase. Alright, we've got a dig plan, which is our puzzle input. Looks like we've got a direction and a distance. Okay, it's like the third day of grids and up, down, left, rights, but okay. Lots of grids, here we go. Yep, should be painted, okay. When viewed from above, the above example dig plan will result in the following loop of trench, okay. So we just got to start at 0, 0, okay, right 6. So 1, 2, 3, 4, 5, 6. Oh, we started 0, 0. So 1, 2, 3, 4, 5, 6. And then down 5. 1, 2, 3, 4, 5. Okay, got it. Not sure how that represents color, but let's keep going. At this point, the trench could contain 38 cubic meters of lava. However, this is just the edge of the lagoon. The next step is to dig out the interior so that this is a 1 meter deep as well. 1 meter deep as well. Now the lagoon can contain much more respectable 62 cubic meters of lava while the interior is dug out. The edges are also painted according to the color code in the dig plan. How many cubic meters of lava could it hold? So let's think about our approaches here. We could just build a grid and we could populate all of the area. We could follow the instruction at 0, 0 and just populate it with hashes. And then we could run some sort of calculation on each point in that is not defined. And then we could try to determine how many points are populated. But I think it's a terrible idea. One, that's not going to scale. And well, these aren't a ton of inputs. And these numbers aren't bad. So maybe that would work. But I don't think it's going to scale. And my hunch kind of tells me that just based on what we did with the gravity, what was it? Day 10, maybe day 9. And a couple of our other problems where they went from simple problems to problems of scale. I think we should approach this a different way. So let's do a little bit of thinking. It's been a while since I've been in school, but I do know that there should be some sort of mathematical equation to calculate the area of a polygon. Okay, here we go. The shoelace formula, also known as Gauss's area formula, and the surveyor's formula, is a mathematical algorithm to determine the area of a simple polygon whose vertices are described by their Cartesian coordinates in the plane. It is called the shoelace formula because of the constant cross-multiplying for the coordinates making up the polygon-like threading shoelaces. It has an application in surveying and forestry, among others. I'm just reading Wikipedia here. The formula was described by Albert Ludwig Friedrich Meister, based on the trapezoid formula, and it looks pretty doable as far as computationally concerned. So, okay, so that's the area. Let's start there. Let's parse this object and let's start picking the area. And I think that'll be close, but I think we might be missing something because if I recall, this is again going back to algebra or geometry. I think that since these are full 1 meter squares, was it meters? Yeah, meters. That when you calculate the area, you're going to get like half of it. So let's, if we can first just calculate the area, see where we're at, and then figure out where we need to go from there. All right, got my hoodie on and I'm ready to implement. First, we don't have a grid per se, and I don't plan on creating a grid. We do have an input, and we need to iterate and then for each line, we are going to have input that looks like this. And I almost forgot about the color. I guess we're not doing anything with the color. So we'll just ignore that for now, I guess. I'm sure coloring boxes will be fun in part 2. So we really just need to split this again. And we'll split it on space. That'll give us the 3 parts. And we've got our direction, which is item sub 0, and our item sub 1, we want it as an integer, and we're going to get back our moves, and we can go ahead and capture the error, and if ER not equal nil, we can panic with the error. It's probably fine. Right, so what we want to do is we want to create I guess a set of points, right? And for what we're going to do here, we're just going to think about it as a slice of int. And the first point is 0, 0. So that's our starting location. If we look here, right, we dig up, down, left, right, etc. But we start at 0, 0. Then I guess what we could do is create a map of string to slice of ints, and we can then define these directions. So up, down, left, right. So we've got up, so that's going to be -1, 0. We've got down, left, right, +1, left, -1, right, +1. All right. So the reason we did that is because the first character, the dir, is going to dictate which way or where we move from where we currently are. So we're at 0, 0. We're going to make some move in some direction. So what we're going to do then is, with the points, we're going to make a set of points. So the way we're going to do that, is by looping through this, and we know we're at 0, 0. So our row is equal to our points minus our length, points -1. So we'll get the last element sub 0, and then the column. So this is getting our current row and column position. And then we're going to use this, and we're going to say that our points equal to points, or append, sorry, points. And then the points are going to be this, and our row is going to be row plus. So we've got our dir, but really honestly, we could just do dir's sub dir. Yeah, we'll do that. And then that way we've got dir sub 0 times moves. And so if our direction is a row is 0, it'll just move 0. That's going to be row plus, and then it's going to be column plus, and we're going to do the same thing. Dir times moves, and if, depending on what direction we're headed in, that will all be fine. I think that's it right there. Okay. Let's get rid of this so we have some more real estate. Right. So now we've got our points, and we're just going to print out our points here and kind of see what we get. I always do printf, but right. I didn't bring my test input in. So let's bring in our test input. Right, here we go. 0, 0, 6, 6, 11, 11. That one almost bit me. This is wrong. This should be 0, -1. And this should be 0, 1. All right. Let's try it again. Right. Okay. That looks good to me. Let's clean this up just because we don't need it. A little cleaner. All right. So now that we have our points, we need to calculate the area. And so let's create a function for that. We'll just call it area. And we'll take in our points, which is a slice of ints. And I think that's all we'll need, because that's all of our points. I think in order to do this calculation, we need to calculate the inverse. So let's do int j equals length of points minus 1. And then we'll do for I actually, let's do this way. Right. And then we will, if we have some value area, and then area can be our points sub j plus our points sub I, so they're adjacent, and then timesing that by our points. Okay, so we want to do sub 0 here and sub 0 here, and then likewise points sub and then we'll do the 1, which will be the column essentially. And so we'll add that together. And then I believe with the formula, we return the ABS, math.abs of area divided by 2. So, I mean, we can work with float 64s. This will just have to be and it's getting uglier by the moment. Yeah, we'll do that. And then that should be our area. $102. Doesn't that sound right? Right. So I see what I did wrong in the formula. It needs to be this. All right, 42. Okay. That's a little bit closer, and I think that's right. So let's go back here. I think that's what I saw. So at this point, the trench could contain 30 cubic meters. However, there's just the edge of the lagoon. So 38. I've got 42 as my area, and I need 62. 2, 3, 4, 5, 6, 7, 8, 9, 10, 30, 40, 52. All right, well, there's 38 of those. And I've got 42. So this is the area, but we can get the boundary. And so the boundary would be anytime we move, like the total number of areas in which we moved, which that's 38. Okay. And 42 is the area. What's 38 plus 42? That's 80. That's not 60. We're looking for 62. Actually, let me update my test. Since we have the input in here. So what is the difference? I think what we're running into is on this boundary here that we've got the total area. What we want is the area of the inside plus the boundary, because I think we're losing some of our area here on the edges. So the way we're going to do that is we're going to calculate the interior. I think it's, I don't know the name of the formula, but the interior should be our, here, let's move this to be area move that, and then we can call area here, and then the interior should be plus, or I'm sorry, minus our boundary divided by 2 plus 1. And because so then what's our interior? Our interior is 24 plus 38, which is our boundary. That's 62. Okay, so then I think it is our interior plus our boundary. You're a float 64, and you're a float 64, and you're a float 64. Everything's a float 64. Boom. Boom, baby. Okay, let's get rid of these print statements just to clean things up. Cool. Let's grab our input. Let's run our test. Or run our program. 62,365. That's it. Awesome. Woo. Got it. All right, let's go into part 2. The elves are right to be concerned. The planned lagoon would be much too small. After a few minutes, someone realizes what happened. Someone swapped the color and instruction parameter. They don't have time to fix the bug. One of them asks if you can extract the correct instructions from the hexadecimal code. Each hexadecimal code is hexadecimal digits long. The first 5 hexadecimal digits encode the distance in meters as a 5-digit hexadecimal number. The last hexadecimal digit encodes the direction to dig. So 0, 1, 0 means R, 1 means D, 2, 3, etc. Okay. So, fine. So in the above example, the hexadecimal codes can be converted into the true instructions are, and then 461937. Okay, do we ignore the, I'm sorry, they inverse this. The first 5 hexadecimal digits, 1, 2, 3, 4, 5, okay. Hexadecimals, basics, 18, right? Yeah. Okay. Got it. Got it. Well, I'm glad we chose to go the math route, because if we had tried to, if our test size is this, I can't imagine what our input is. Okay. So, got it. All right, let's do this then. This should be pretty straightforward. How do we want to do this as far as implementing? I think in this case, I'll go ahead and do a part 2. Even though what I think I'll do instead is, well, yeah, because most of this is just the parsing. Really, these last couple of lines here. Yeah, we'll just create a part 2. I think at this point I feel comfortable enough with that. Again, it's duplication of code, but I'd rather have, my goal here with the AOC is that I have complete working sets of part 1 and part 2 in the repository. So it's a little bit less about cleanliness and more about just execution of code and rerunability, maybe for future use or just for whatever. So we'll just call it a part 2. We'll call part 2 here. Nothing crazy there. And then we're going to change this. We're just going to add to it. So we'll get these mappings, and 0, 1 means down, 2 means left, 3 means up. Okay. And we'll just do that. Instead of we could do a map of direction. That's just fine. So none of this has to change. The only thing that has to change is the way that we parse. So I think the answer becomes we split and get the third. So our initial input we ignored. We just looked at these first 2. Now we're going to get this third part. And so we can call it instruction item sub 3. All right, so that should just strip the parentheses off. And then we actually don't need the pound sign either. So I'm going to just move it to a 2. And let's just see what that is. We can make this, no, this should be fine, because we broke it apart into 2 separate things. Like 3. Oh, because it's 2. It's not 3. It's 2. Right. Appendix 70C 71 70C 71. Let's look here. Well, that's 70C 71. Okay. I always forget that when we're working with those, it's length and not the index of the end position. And it bites me every time. And I don't know if I will ever get that right. Okay, so that's what we want here. So that's our number. So that's good. So then we can split this apart one last time. So the DIR's, the direction is going to be the instruction, and it's going to be the length of inst minus 1, and the moves are going to be 0 to the length of inst minus 2. So we're going to go one less character, or minus 1, because again, this is length of character. So that is what we want. We want everything except for the last. And then we're going to just panic. Let me panic dir, and then this pink. There's a thumbed up panic. We'll do a print line. So did this fail on 101? Okay, 5 and 1. Can I just do that? Yeah, invalid syntax, that's fine. Where's my print line? 70C71. 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 Okay, cool. So let's change this to a parse int. Was it parse int? And then we can give it the string. And we can give it a 16. I don't know the bit size is, I think, just 0. And this should give us pretty much the same thing here. We'll get past that here in a second. Yeah, we're just gonna do this here so we have less pain later. Maybe less pain. I guess we could exceed the boundary there. Okay, cool. So we've got our direction and we've got our values. Okay, so we can get rid of this print then. That's perfect. And our test pass. All right, awesome. So do we put our value? Yes. All right, that really should be it. Let's try part 2. To actually call part 2. Because this is all math, this should really be just as fast for a number that high. Let's give it a shot. Awesome. We've finished up. So let's go back and just do a brief recap of the solution, the problem in the solution. So for day 18, we ended up with a set of inputs that drew a polygon. So in this case, the left was the reverse character was the direction. So whether we're on right, down, left, up, and the number of spaces. And then from that, we would draw a polygon and we would have to tell what the total number of area is. And the tricky part is when you do area, you lose a little bit of the total of the boundary, and because it's in the middle of the boundary, but we know that that's a full square or full cubic meter. So then we have to look at the boundary, but that's not enough because you end up at some cases like here or some cases like here where the amount of extra that we get differs. So then the solution is to use an algorithm to calculate the center bit. And when we calculate the interior area, we can then add on to that the boundary. And that gives us our total, which was here 62. And then for part 2, since we can do that mathematically, it was the same thing, except we were using this parsed out value here to get a new direction, which was the last character, and then the base 16 or hexadecimal rather, value, and which gave us a much larger number. And because this was all math, it executes very quickly. So let's look at implementation. I first had a DIRS map that just mapped a given up, down, left, right, or later 3120 to a row column add subtract map. Then for part 1, we built our set of points based on the input. That's what this is here, just parsing through, ripping out those values and creating a slice of ints so that you would have a slice of slice event, and each slice event was row column. And so you could loop through that. That gets passed to this polygon area function, which just calculates the inverses and essentially turns every set of points into triangles to calculate the full area. And since it's technically calculating double the amount, you have to divide it by 2. I think this is referred to as the shoelace formula because of all the crossing. And then part 2 was, again, the exact same thing. The difference was in how you parse the input. A little bit more challenging because we're doing some base 16 parsing, not a big deal, and some calculations, but the calculations at the end are exactly the same. So you can see that number is really high. I know I talked about in the initial video, maybe we just draw out the grid and count the area, but while they may have worked for 62,000, it would not have worked for 15 trillion. Yeah, I mean, I'm sure we would have eventually calculated it, but all right, well, that's all I have for tonight. I'll see you next time. And as always, over and out.